you need to know of the conservation of charge, lepton number, baryon number, and strangeness. Okay, conservation means that what you start off with is what you end up with. Now, for each reaction you are presented with, you need to check for the conservation of charge, lepton number, baryon number, and strangeness. You will need the data booklet to help you do this. So remember charge, lepton number, baryon number, and strangeness. Now, what is a charge on a neutron? It's 0. What is a charge on a proton? It's +1. What's the charge of an electron? It's -1. So 0 goes to 1 and -1. So they're conserved. Lepton number. Well, the neutron is not a lepton, the proton is not a lepton, but the electron is a lepton. It's a light particle. So we end up with an imbalance here. So as it stands, this would not work. This doesn't obey the rules. Let's carry on. Baryon number. Well, the neutron is a baryon, the proton is a baryon, and the electron is not a baryon, so 1 is equal to 1 plus 0. That's all well and good. Strangeness. Well, the neutron does not have any strange quarks, neither does the proton, and the electron is not even a quark, so that will be 0 too. Now, as it stands, this is a problem because the lepton number is not conserved. So according to the laws of conservation, this could not happen. The only way it could happen is if we had another particle that was produced which had a lepton number of -1 to balance this. And this is how they did it. This is how they work out the particles that are missing. They say there must be another particle here which has a lepton number of -1. This particle must have 0 charge, it must have -1 lepton number, it must have a baryon charge of 0, and it has a strangeness of 0. In fact, there is one particle which fits this description, and that's basically an anti-neutrino. Notice that an electron is produced with an electron antineutrino. So now this works. Now, as I said before, for each reaction you're presented with, you need to check for conservation of charge, lepton number, baryon number, and strangeness. Let's look at this. Will this work? Charge, lepton number, baryon number, strangeness. Well, the charge starts off with -1, goes to -1. This is no charge, this is no charge. -1 goes to -1, which works. Lepton number. Well, the mu minus is a lepton. The electron is a lepton. The antineutrino is an anti-electron, and that one, the last one, is a mu neutrino, which has a lepton number of 1. So we have 1 is equal to 1 plus -1 plus 1, and that works because 1 is equal to 1. Baryon number, well, these are leptons, they're not baryons, so that's an easy one. And strangeness, they're not quarks, so there's no strangeness there. So all of these work. So this interaction could happen. These are leptons, so it will happen by the weak force. What about a down and an anti-up? And it does this. The pion, pi minus, is a down and anti-up. Let's try and look at this. What is the charge, the lepton number, the baryon number, and the strangeness? The charge is -1. This is -1, and this has no charge. So that works. The lepton number, well, the pi minus is a meson. It doesn't have a lepton number. Well, the lepton number is 0. This is a lepton, and this is an anti-lepton, so that's a 1 and -1. So that is also consistent. Baryon number. This has a baryon number of 1/3 plus -1/3, which is 0. And these are leptons, so they have no baryon number. Strangeness. Well, this is down and anti-up. There are no strange quarks here, so that's going to be 0 as well. So this interaction could also take place. Let's look at this. A K0 and a proton interact to produce a K plus and a neutron. Let's look at the charge. You can work out the charge here, but also this is going to be 0, that's plus 1, that's plus 1, and that's 0. So it's going to be 1 on each side. That works. Lepton number. Neither of these are leptons. They're hadrons. We've got mesons and baryons here. Baryon number. This has a baryon number of 0. This has 1, 0, 1. So that works. Strangeness. Now this has anti-strange here. This is anti-strange. So this is consistent as well. So this has plus 1 and this has plus 1. So that works. So this interaction would also take place. However, it would only take place with the strong force, not with the weak force, because the strangeness is conserved. And this one, we have a lambda 0 decays to a proton and a pi minus. Charge, lepton number, baryon number, and strangeness. This is 0 goes to 1 plus negative 1, so that is consistent. Yes, that works. Lepton number, these are hadrons, not leptons. Baryon number, this is a baryon number of 1, this has a baryon number of 1, and this is a baryon number of 0, so that works. Strangeness, well, we start off with a strange particle here, but there are no strange particles there, so that's going to be 1, and negative 1, and it goes to 0. So strangeness is not conserved. However, it is possible that you have an interaction where the strangeness is not conserved, but this interaction will happen via the weak force, not via the strong force. So, in this case, strangeness is not conserved. This, however, could happen because strangeness is conserved in strong force interactions and not in weak force interactions. You need to be able to do these fairly quickly. So, summary. Charge, lepton number, baryon number, and strangeness are all conserved for the reaction to take place. In the exception when strangeness is not conserved, it must be with a weak interaction.